Hi everyone. In this video I'm going to show you how to create a plot of stress and strain. We are given this information. These loads are applied to a tensile sample and the gauge length has been measured during the tensile test. So the original gauge length is 2 inches. As we increase the load, the gauge length is increasing and at this point rupture happens. Now the original diameter of the sample is also given as 0.505 inches and diameter at rupture is also given as 0.47 inches. These are the unknowns that are asked in this problem. Once we create the plot for stress and strain, we can obtain all these parameters from that plot. So now, first step is to find stress corresponding to each of these loads. Remember that stress is load divided by the original area. Calculate the cross-sectional area at the start of the experiment. I'm going to calculate the cross-sectional area here. So I've been given this original diameter, and cross-sectional area is pi times diameter to the power of 2 divided by 4. So I'm going to add this formula here. Pi times original diameter to the power of 2 divided by 4. So 0.2003 inches squared is the original cross-sectional area. Now that I have this original cross-sectional area, I can divide each of these loads and find the stress at any of these points. So I'm going to create a column here. So stress, which would be in PSI, because the load is given in pound and gauge length is given in inches, diameter is given in inches, so stress would be pound per square inch. So I'm going to add the equation here, stress divided by the original cross-sectional area that we obtained here. So I'm going to put this number here, 0.2203, 0.2003. Drag this autofill handle, and here we have stress corresponding to each of these loads provided here. Next column, I'm going to create strain. Strain is a dimensionless quantity, and remember that strain is changes in length, so elongation divided by the original length. So the original length of our sample is 2 inches. So for each of these gauge length, I need to subtract 2 from this gauge length and then divide the result by 2. So here I'm going to add the equation for strain. So gauge length. So let's open a parenthesis first. Gauge length minus 2 inches, close the parenthesis, divided by 2. Now let's make the decimal points consistent. So 4 decimal points is good. Now I have strain corresponding to each of these stress that I obtained in this column. Now also let's reduce the decimal places here. And now in this column I'm going to calculate elastic modulus. So remember from Hooke's law, elastic modulus is equal to stress divided by strain. And as strain is dimensionless, So elastic modulus would also be in PSI units. So let's add the equation here. For the first row, let's start from next row. So elastic modulus is stress divided by strain. Now I don't want to divide 0 by 0, so I will start from here. So equal sign stress divided by strain. Enter. Drag this autofill handle, and here let's convert this to scientific notation format. Now, if you notice, you can see that for the first four answer that we got here, we have the same number, and for the rest, we have different values. We're gonna get rid of this part because elastic modulus is only applicable to the linear portion of the curve. And from this data, it is obvious that from this point, there is no such relation between stress and strain. So let's get rid of this part. And now we can make sure that up to this stress point, we are in elastic region. And above this stress, we enter the plastic region. Now let's type elastic here. Also, let's highlight this part for the elastic region, and this part which refers to the plastic region. Let's go ahead and create the stress-strain plot. So I'm gonna use the Insert tab. From the chart type, I would select this scatter type. So inside the chart, right click and click on select data, add stress versus strain. For X values, I'm going to select strain. For Y values, select stress. Click OK, OK. And here we have the plot. So now let's add the axis title. This is strain. And y-axis is stress in PSI. So if you notice, you can see that in it starts a linear relation between stress and strain, and at some point it converts to, and there's a transition from linear to non-linear. Now let's complete some of the unknowns that we already found here. So for elastic modulus, we got 2 times 10 to the 7 psi. So I'm going to add this here, 2e7. For 0.2% yield strength, we're going to discuss in a minute. Ultimate tensile strength would be the maximum stress withstood by the sample. So that would be somewhere between 50,000 and 60,000 psi. Now let's add the formula here, equal sign max, open the parentheses, and include the entire column of stress inside parentheses. So the ultimate tensile strength is 53,919 psi. This value here. Percent elongation would be the elongation of the sample when the rupture happens, multiplied by 100. So here I'm going to add the equation. Select this cell, multiplied by 100. So we have 0.85% elongation in the sample. Percentage of reduction in area. So let's calculate the cross-sectional area when the rupture happens. So I added this here, area at rupture. So for this one, we need to use the diameter when the rupture happens. So put the equal sign, pi times diameter to the power of 2 divided by 4. So 0.17349 inches squared is the area when the rupture happens. Now let's add the equation here, equal sign original area, let's open a parenthesis, original area minus area at rupture, close the parenthesis, divided by original area. So let's increase the decimal points. So here I also need to multiply this by 100. So we have 13.38% in reduction of area. Proportional limit, that would be the point that stress transition from linear to non-linear. So if you look at this plot here, that happens at this point, and here from the table you can also find it here. So the transition from elastic to plastic, that would be the proportional limit. So I'm going to add this number here, 19,970.04, enter. So 19,970 psi is the proportional limit for this sample. Next, let's go ahead and find the 0.2% offset yield strength of the sample. So here we need to create a straight line which is parallel to this linear portion of the curve and starts from 0.002. So once you have 2 points, you can you can find the equation that connects the two lines and find the equation of the straight line. So here I'm going to use these 2 points. One of them would have the coordinate of 0.002 and 0, and the other one I can we can try 0.004 and find the y coordinate of that point. So let's put this would be 0.2% offset strain, and this one would be 0.2% offset stress. So I have 0.002 and 0. This is one of the points. The other point, let's try 0.004. Now remember that the straight line that connects these 2 points has the same slope as the elastic modulus that we obtained here. So now here, if I want to find this the y coordinate of this point, that would follow this equation. So I would put a single quotation mark here to consider this as a text, not as an equation. So elastic modulus times x2 minus x1. So that would give me the y coordinate at this point. Now I'm going to add the equation. Equal sign 2 times 10 to the 7 times, open the parentheses, x2 minus x1, close the parentheses, enter. So that would return 40,000. Now let's plot these 2 points. So I'm gonna add a series to this plot. Select data, add, offset, for x values, let's select these 2 points. For y values, let's select y coordinates. Click OK. OK. Now I have these 2 points, and let's add a line here. So format data series, add a solid line. So this is a line that connects the 2 points, and if you notice, you can see that this straight line has the same slope as this linear portion of the curve. Now we need to find another point because it's not intersecting with the curve here. Also, let's add a line to this curve. So click on one of the points, format data series, add a solid line, now let's try 0.005. So for this one, we could get a y coordinate somewhere here. So let's try. So notice that y coordinate would be 60,000, and there's an intersection here. If I go to chart design and select this one which has grid lines, I can estimate where the extraction is, where the intersection is. So Here it looks like it is about 47,000. So let's type 47,000 here. So that would be 0.2% offset yield strength of this material that we obtained from this intersection between these two lines. So this is how we create the stress-strain curve, and from the stress-strain curve, this is how we get all this information. I hope you find this video useful, and thank you.